Now I expect you to ask, what if our x and y are dependent on more than one variable? So this is the second part of the chain rule, which says, let z be the function f of x and y, be differentiable as usual, as before. Be a differential function, but now your x is g of s and t. Guys, note that I'm adding a new variable. In previous case, you only had one variable. Now I'm adding a new variable s. And also y is h of s and t. I'm introducing a new variable. So your variables x and y are also functions of two other parameters, are differentiable functions. So now you can find the rate of change of z with respect to t, and also the rate of change of z with respect to s. We are introducing two new variables, so now we are taking the partial derivatives. This guy is going to be partial derivative of z with respect to x, partial derivative of x with respect to t, plus partial derivative of z with respect to y times partial derivative of y with respect to t. Partial derivative of z with respect to s is going to be partial derivative of z with respect to x times partial derivative of x with respect to s plus partial derivative of z with respect to y times partial derivative of y with respect to s. This is your second part of the chain. Take a look at the following example. Let z be exponential function e to power x times sine y. X is defined as st squared and y is defined as s squared times t. You want to know what are the partial derivatives of z with respect to t and s. Okay, again, you have the first option, plug in x and y here for the function. So you get e to power st squared sine of s squared t, and then take the partial derivative with respect to t with respect to s, or just follow the formula. So first option is just substitution. The second option is using the formula, whichever is easier to use, easier to follow. Partial derivative of z with respect to time, or t, in this case is partial derivative of z with respect to x. So you get e to the x sine y. Guys, when you're taking the partial derivative with respect to x, your y is just a constant. It means that sine of y is just a constant. And multiply this guy with partial derivative of x with respect to t, which is 2st, plus partial derivative of z with respect to y, which is e to power x cosine y, times partial derivative of y with respect to t, which is s squared. Are we done yet? Nope. Why is that? Because we are taking the partial derivative of z with respect to t, but here we have x and y present. It's not acceptable to have these variables. So just do the substitution. E to power s t squared sine of s squared t times 2st plus e to power st squared cosine s squared t times s squared. Simplify if it's necessary, and if you can, just simplify this more. Good, we can just get rid of some of the parentheses here. We don't need that many parentheses because there is no addition here, so just leave it as it is. You might say that, hey, I want to factor out s squared e to power st squared. Yes, go for it. You can write it in factor form or just leave it as it is. The partial derivative of z with respect to s. Now we are following the second formula. Partial derivative of z with respect to x, which is e to the x sine y, times partial derivative of x with respect to s, which is t squared. Plus, now partial derivative of z with respect to y, which is e to the x cosine y, times the partial derivative of y with respect to s, which is 2st. Again, don't forget to do the substitution. We cannot have x and y present here. Here you have e to power s t squared sine of s squared t times t squared plus e to s t squared cosine of s squared t times 2st. Again, you can factor out e to power s t squared. You can factor out t as well and write it in factor form, or you can just leave it as it is.